is the kind of setting which may have inspired early man to develop some of the beginning ideas of number. How many sheep do you see in this pasture? A way to answer this question may seem obvious to you, but it was not obvious to a shepherd of long ago, whose people had not yet developed any language of number or any formal arithmetic. In fact, there are still some primitive societies in existence where there are no words for numbers greater than 2. Young children of our own culture begin their understanding of arithmetic at about this primitive level. Let's go ask some young children our question about how many sheep. Hello. Hi there. Hi, I have something. Okay. Hello, Sad. Sad, you feeding sheep?
Yeah.
I want to ask you something, Sad. How many?
1,
How many?
2.
I'm going to ask you something else now. How many sheep?
Lots of sheep.
A whole bunch, isn't it? And we have to feed all of those sheep. When children first come to school, they bring with them some primitive notions about numbers. We are then given the task of teaching them a great deal of mathematics, some of which took the human race thousands of years to develop. I'd like to consider with you the important beginning stages of a program for developing mathematical concepts. In particular, let us consider these 3 basic ideas of mathematics. One-to-one correspondence, number, and counting. Let's view our pastoral scene again. How could you answer the question, how many sheep, without counting and without using any special number words or symbols? You would be likely to work out a method similar to that used by a primitive shepherd. You might arrange to have the sheep file past you. And then, for each sheep, you would set aside a convenient object, such as a pebble. 1 sheep, 1 pebble. Another sheep, another pebble. Another sheep, another pebble. By this process of matching, you would then end up with a set of pebbles to match the set of sheep. The set of pebbles provides a convenient method for answering the question, how many sheep? There are this many. The pebbles also serve for keeping a record of how many, so that the flock can be checked at another time to see if any of the sheep are missing. The same one-to-one matching technique is used by the preschool child when he asks his mother for some cookies. He is given a cookie for himself, and then he asks for a cookie for each of his friends. I want this many cookies, he says. In this kind of situation, fingers are more convenient than pebbles to indicate how many. Both the primitive shepherd and the young child can clearly deal with the question of how many without any formal knowledge of numbers. The process of matching used by the shepherd and by the child established what is known as a one-to-one correspondence between 2 sets. The term set is used in mathematics when referring to a collection or a group of objects. Teachers have always used sets in developing number concepts with children. Before numbers are associated with sets, however, some basic notions about sets themselves should be established. Let's visit a kindergarten class and see how some ideas about sets are used to build a foundation for work with numbers. We find out for sure if there are as many turtles as fish. And Michael, you said that you could show us how to do this. Will you show us, Michael? Maybe you can stand over on the side a little bit so they can see what you're doing. All right. Oh. Are there as many turtles as fish? Yes. What can we say about sets that match this way, where there are the same number in one set as in the other set? Do you remember what we say about those sets, Michael? What kind of sets are these?
Equivalent.
Yes. And I wonder, I'll tell you what we're going to do. We'll take a little trip, but you'll have to close your eyes. And you imagine that we're taking a trip out to the farm, and I'm going to show 2 more sets, but you have to close your eyes because I don't want you to see these sets until I ask you to open your eyes. All right? Close your eyes. Good. All right, open your eyes. We have a set of horses and a set of pigs. Are there as many pigs in this set? Are there as many pigs as horses?
Yes.
Let's find out if these sets are equivalent. Who would like to match these sets? Would you like to match them? Put a pig with every horse and we'll see what happens. Go slow. And stand back a little bit so they can see you. That's right. Oh, do you want to sit down so we can see? Was there a pig for every horse?
No.
Are there any pigs left over?
Yes.
Are these sets equivalent? Do they match?
No.
Do you know what we say when sets do not match? What kind of sets we say they are? We say they are, oh, it's very easy. They are not equivalent. Could you say that? They are not equivalent. Yes. And I want to see whether, let's see whether you can tell if these sets are equivalent just by looking. But first you have to close your eyes so I can put the sets up. All right. Don't open your eyes yet. Don't open your eyes. All right, open your eyes. Here's a set of circle shapes, and here's a set of square shapes. Are these 2 sets equivalent?
No.
What could you say about these 2 sets?
1 and 2.
What would you say? No numbers today.
They're not the same.
They're not, that's right. They're not
equivalent.
That's just right. Now let us go over some of the fundamental notions about sets and about one-to-one correspondence that are basic to a child's understanding of number. First, the notion of sets. Any specified collection of objects may be considered as a set. We'll label the sets shown on the board A, B, C, and D so that we may refer to them conveniently. Now, any object in a set may be referred to as a member or as an element of the set. Next, the notion of matching. Matching may be thought of as a pairing off process, which may be used to determine whether one set has as many elements as another set. The matching may be considered or carried out in different ways. Let's use sets A and B to illustrate. We'll select any member of B. We'll consider pairing it off with any member of A. Select another member of B, pair it off with another member of A. And when we have gone as far as we can in the matching process with these two sets, we find that for each element in A, there is an element in B. And for each element in B, there is an element in A. There is no element left unpaired. No unpaired element left over in either set. Now, suppose we tried matching a different way. Let's see what would happen. We'll choose different pairs this time, and we'll match in this manner. We get the same result. That is, there is no unpaired element left over in either set. This leads us to another idea. The idea of one-to-one correspondence. When two sets are matched in the manner just illustrated, that is, if to each element of one set there corresponds an element in the other set, and vice versa, the two sets are said to be in a one-to-one correspondence. Sets that are in a one-to-one correspondence are said to be equivalent. Sets A and B are in a one-to-one correspondence, so A and B are equivalent sets. We can show that sets A and C can be put in a one-to-one correspondence. So sets A and C are equivalent sets. We could also show that sets A and D cannot be put in a one-to-one correspondence, so A and D are not equivalent. We have talked about sets and about one-to-one correspondence. We will now see how these ideas about sets and one-to-one correspondence can be built upon in developing the idea of number. Let's look at our sets A, B, and C again. Aside from the fact that all of these sets contain elements, what do these sets have in common? It seems obvious. They all have the same number of elements, and the number of elements is 3. But to the young child, what do we mean by number? And what do we mean by 3? In the beginning stages of learning, it isn't obvious that there is something in common between a set of 3 sheep and, let's say, a set of 3 eggs, or between a set of 3 birds and a set of 3 people. It must have taken the human race a long time to develop the concept that there is something in common between equivalent sets. In order to convey the notion of how many objects there are in a set, an idea called a number is assigned to the set. If we were to use set A to develop a particular number idea, we would begin by having children associate the number 3 with set A. We would then have them associate the same idea, that is, the number 3, with various sets that they could match with set A. In this manner, children build toward the generalization that if any set is known to have 3 elements, then any set equivalent to it also has 3 elements. Children then learn to generalize further that all sets equivalent to the same set are assigned the same number. They also learn that sets that are not equivalent must be assigned different numbers. Now we have established a basis for an understanding of the idea of number. But how do we communicate this idea? A number may be represented in different ways. Here are some words for the number 3. The words are different. They are from different languages: French, German, Spanish, Russian, English. But all these words name the same number. Here are some special symbols for the number 3. A symbol used to name a specific number is called a numeral. Here is a Roman numeral for 3. Here's an early Greek numeral, a Hebrew numeral, a Chinese numeral, and the familiar Hindu-Arabic numeral. These numerals are different, but they all name the same number. So far then, we may think of number as a property of sets, and we may think of a numeral as any symbol used to represent a number. Children can learn which numerals go with which numbers with the help of what might be called representative sets. Here are some sets which could be used as representative sets. A child can determine the number of elements in a particular set, let's say this set, by finding the matching representative set. Now let's see what ideas might be brought out if a child were to try to match 2 of these sets. Let's say these 2. For each object in one set, the child picks a partner in the other set. This set has some objects left over. There are no partners for them in the other set. No matter which way the child carries out the one-to-one matching process, there will be unpaired objects left over in this set. When we try matching 2 sets and find that they cannot be made to match, we will say that the set which has unpaired objects left over has more objects, while the other set has fewer objects. Now let's compare the numbers associated with these sets. The number of the set which has more objects is, in this case, 5. The number of the set which has fewer objects is 3. We say that the number 5 is greater than the number 3. To put the idea another way, we say that the number 3 is less than the number 5. Here's the mathematical notation for these 2 expressions. 5 is greater than 3, and 3 is less than 5. Notice that the special symbol opens out toward the name of the number that is greater and points toward the name of the number that is less. Suppose we arrange our representative sets in such a way that the number of elements in each set is less than the number of elements in the succeeding set. We'll begin with the set which has fewer elements than any of the other sets. Next, the set which has more elements than this set, but fewer than any of the others. This works out, as we continue, so that each succeeding set has one more element than the preceding set. We can imagine that this pattern continues indefinitely. Now let's consider the numbers associated with these sets. One, 2, 3, 4, 5, and so on. We now have an order for the numbers corresponding to the order for the sets. In the order we established for the sets, each set has fewer elements than the succeeding set. It follows that the corresponding numbers are in an order such that each number is less than the succeeding number. Therefore, we may write 1 is less than 2, 2 is less than 3, 3 is less than 4, and so on. We shall now show how this ordering of numbers helps us to determine the number of elements in a set. We could begin by thinking of a set consisting of just the number 1. Every set equivalent to this set will, of course, have one element. Then we'll consider the set consisting of the number 1 and the next number, 2. How many elements does it have? We'll consider the numbers 1, 2, and 3 as forming the next set. How many elements does it have? Soon a pattern becomes apparent. When we consider any set of successive numbers in the order we have just indicated, beginning with the number 1, what happens? 1, 2, 3, 4. There are 4 elements in this set. 1, 2, 3, 4, 5. There are 5 elements in this set. The last number in the sequence is the number of elements in the set. At first, children may have trouble using the counting numbers. If you ask a young child to count the apples in the basket, he might do this. 1, 2, 3, 4, 5, 6, 7. Or he might do this. 1, 2, 3, 6, 7. He could get the same wrong answer for 2 different reasons. In the first case, there was not a 1-to-1 matching. In the second case, the numbers were not matched in the proper counting order. You can see that before numbers and counting become meaningful, the concept of 1-to-1 correspondence must be established. Let's watch a child use the counting numbers to determine how many elements are in a set. This child is matching the elements in a set of cutout figures with the counting numbers as represented on what is called a number line. An element in a set is matched with the first counting number, another element with the next counting number, and so on. When each object in the set has been matched with a counting number in this manner, the last counting number used in the matching process is the number of elements in the set. Generally, we begin counting with the number 1. In this space age, however, children are familiar with the countdown procedure used in rocket launchings, and even kindergartners know a number which comes before 1, though they may call this number blast off instead of 0. To develop the concept of 0 as a number, we once again make use of sets. Here are 2 baskets used for holding fruit. Let us consider the set of fruit in each of the baskets. One set has as its members an orange and 2 lemons. Its number is 3. But what about this set? The basket is empty, so we may think of this set as an empty set. The number of elements in this empty set is said to be 0. exercises involving arrangements such as shown on this board, where children are to apply number labels to sets, help to establish the idea of 0 as a number. We have called the numbers 1, 2, 3, 4, and so on the counting numbers. When 0 is included, we will refer to these numbers as the whole numbers. In this session, we have presented an introduction to 3 basic ideas of mathematics. One-to-one correspondence, number, and counting. We have suggested that in developing these ideas, children generally go through somewhat the same stages that the human race has gone through. This would indicate that we should be wary of moving too quickly in building beginning number concepts. All of these ideas are basic not only to elementary school mathematics, but to more advanced levels of mathematics as well. In their later work in mathematics, pupils will find that the idea of number is extended to include, besides the whole numbers, negative numbers, rational numbers, and irrational numbers. Pupils will learn that a one-to-one correspondence can be established between the set of all of these numbers, the rational and the irrational, and the set of all the points on a line. One-to-one correspondence and number are basic concepts in mathematics, whether it is the kind used in the counting of sheep or in the planning of expeditions into outer space. We believe that the most effective way to teach mathematics is to teach basic concepts in a way that will build understanding, the kind of understanding that will enable a child to figure out solutions to problems that we think he is likely to encounter, as well as problems we can't even begin to anticipate.